will speak on the Heisenberg Algebra in symplectic algebraic geometry.
Right. Thanks very much for the invitation to speak. It's a pleasure to be here. So what I would like to do in this talk is give kind of an extended example, which is just a small part of a much bigger story. So in the last 20 to 25 years, a lot of work in geometric representation theory has involved constructing actions of natural objects in Lie theory, semi-simple Lie algebras, Weil groups, things like this, constructing actions of such objects on cohomology of algebraic varieties, cohomology of moduli spaces, various things like this. So there's tons of examples of very beautiful constructions which allow you to formulate basic problems in representation theory in a geometric language. What's a bit more recent, I mean, the ideas maybe are quite old, but in the last decade or so, many mathematicians have kind of revisited these constructions and lifted them one level on the categorical ladder, categorified them. So instead of considering a vector space like the cohomology of an algebraic variety, they consider instead some natural category, some category of sheaves associated to the variety. And then sort of try to mimic the original construction in this categorical language, and then ask what sort of new structure you get. And now this is kind of this part of geometric representation theory is growing quite rapidly, and it's very rich. And so what I want to do in this talk is kind of give you one example in an attempt to highlight what sort of structure exists more broadly. Okay, so so the example I want to talk about is related to some of the important objects in Lie theory. So let's start by let's let gamma be a finite subgroup of SL2C. Finite subgroup, which for convenience I'll assume is not trivial. So the basic algebraic object, which will be the organizing player for the entire talk, is an infinite dimensional algebra called a Heisenberg algebra associated to gamma. So the first thing I'll do is define. So to gamma, we'll assign a Heisenberg algebra, which I'll define in a moment. The definition takes a couple steps. So I want to tell you what this object is and then explain how it arises in geometry. So first of all, to gamma, you can associate a finite graph called the Mackay graph. So a finite graph consisting of a vertex set I and an edge set E. And how does this go? So the vertex set is, well, you take one vertex for each irreducible representation of gamma. So you have some finite group. It has irreducible representations. Representations are all always over the complex numbers. So for each, I take a vertex for each irreducible representation. And now for edges, well, if I and j are vertices, distinct vertices corresponding to irreducible representations of gamma, vi and vj, then what I look at, and I want to figure out how many edges to put between these two vertices, I look at the dimension of the space of gamma homomorphisms from vi to, well, not to vj. I mean, these are distinct irreducibles, so there are no homomorphisms between them. But this gamma sits inside SL2C, so there's a distinguished two-dimensional representation of gamma coming from its inclusion. So you take homomorphisms from vi to vj tensored with this distinguished two-dimensional representation. So this dimension is either going to be 0, 1, or 2. It'll only be 2 when I and j are the same. So if we're talking about distinct vertices, then this dimension will either be 0 or 1. So if the dimension is 0, I don't put an edge there. And if the dimension is 1, I do put an edge there. So a priori, this looks like a directed relationship since I and j do not appear symmetrically here. But in fact, this is a symmetric relationship. So you don't need orientation. So the dimension of this Hom space tells you how many edges to put between I and j. So I mean, just for example, let's say you have the cyclic group z mod n z, which just choose an nth root of 1, primitive nth root of 1, and embed into SL2C like this. well, then the graph you get is just an n cycle. And this n cycle has a distinguished vertex corresponding to the vertex corresponding to the trivial representation. So actually both the full graph, which is called the full graph you get here, the graphs you get are graphs obtained in this way. This was the observation of Mackay around 1980. In this way, are the what are called the simply laced affine Dynkin diagrams. And that's if you include the vertex corresponding to the trivial representation. If you just erase this vertex and consider the subgraph, which in this case would just be a chain, then the diagrams you get are not the affine Dynkin diagrams, rather the finite type Dynkin diagrams. Okay. So starting from a finite subgroup, you get a finite graph. So to this finite graph, in other words, to the finite subgroup, you can associate a lattice. So define a lattice. Well, as an abelian group, it's just going to be a free abelian group of rank the number of vertices of the diagram, and you equip it with a bilinear form by, if you have vertex I and vertex j, the pairing of I and j is defined to be 2 if I equals j, minus 1 if I and j are connected by an edge in the Dynkin diagram, and 0 if they're distinct and not connected by an edge. So this is a lattice. So to any finite subgroup of SL2C, we've associated a lattice. And now to any lattice, there is so to this setup, there are several algebras which appear naturally. One is the semi-simple complex Lie algebras associated to these Dynkin diagrams. So that is, for the moment, not the algebras that I want to consider. Instead, what I want to consider is another class of algebras associated to these finite subgroups called the lattice Heisenberg algebras. Okay, so we have this lattice, and I have to tell you what the Heisenberg algebra is. So define a unital algebra. This is over the complex numbers with generators. Well, the generators, you take countably many generators. So for every vertex and every non-zero integer, I take a generator. So I'll call a sub in. The subscript tells me the vertex. So I take these generators, and the relations in this algebra are the sort of canonical commutation relations you see in quantum mechanics, essentially. So basically, if I want to figure out if I want to look at AIN and AJM, these almost always commute with one another. But not all the time. So when n equals minus m, they don't commute. So AI2 and AJ minus 2 might not commute. And then their failure to commute is controlled by the connectivity of I and j in the graph. So these are the relations in what's called the. So this defines an infinite dimensional algebra called the Heisenberg algebra. So right, H gamma is Heisenberg algebra associated to gamma. And actually, I mean, technically, I could do this I could look at generators for all nodes in this graph. Or I could just look at the Heisenberg algebra corresponding to the nodes that don't, other than this distinguished node. So forget the trivial representation of gamma. So actually, there's a small Heisenberg algebra and a big one. So let's say that I'll try to be consistent. So this, if I just look at the non-trivial nodes, then I won't put a hat on the algebra, and if I include the trivial nodes, I'll put a hat on the algebra. Okay, well, I mean, so this is just some algebra defined by generators and relations. It's not immediately clear why it's interesting, but one reason we care, there are a couple reasons to care about this algebra. One is they arise naturally when you consider representations of infinite dimensional Lie algebras. Many infinite dimensional Lie algebras contain these Heisenberg algebras as subalgebras. And these algebras are fairly easy to understand. So if you have some complicated representation of a complicated infinite dimensional Lie algebra and you want to understand it, one thing you might try to do is find a suitable copy of the Heisenberg algebra sitting inside and restrict your representation to this Heisenberg algebra. And then if you understand how it decomposes, that tells you quite a lot about the original representation. I mean, in particular, one sense in which these algebras are easy to understand is they have a canonical representation called the Fock space representation. So H gamma has a natural representation, call it F, which is defined as follows. So, okay, so let's just say you take so I'll write it and then explain it. Okay, so by H minus gamma, I just mean the subalgebra generated by AIN with n less than 0. So just take half of the generators, the negative ones. Let's say that's an algebra. It has a trivial representation, a one-dimensional representation where the unit acts by 1 and all of these other a's act by 0. So you can induce that representation from this kind of lower half to the entire thing. That's called the Fock space representation. As a vector space, it's just a vector space. It looks like polynomial algebra in the AINs for n greater than 0. So, okay, now let's write down. I mean, so this representation is, as a vector space, it's actually a z-graded vector space. Where you just declare the generator AIN to have degree n. And so then you can ask what the graded dimension of this space is. And the graded dimension of the Fock space, by which I mean the sum of the dimension of the mth graded piece times, say, z to the m. Well, so this is the graded dimension. K equals 1 to infinity. So it's the generating function for all partitions, and but then there's one copy of this generating function for all partitions for each vertex of your diagram. So this graded vector space occurs in many places in mathematics, and anytime you see it, you can ask if this Heisenberg algebra is sitting behind the scenes. So an example of an occurrence of this graded dimension elsewhere in mathematics is in the geometry of Hilbert schemes of points on a surface. And so that's now where the really interesting math starts. So I want to explain that. So, okay, so to this finite subgroup of SL2C, there is also some geometry. So you can, in particular, you have a finite subgroup of SL2C, so it acts naturally on C2. So you can consider the quotient space, C2 mod gamma. This is called a Kleinian singularity, or a simple singularity. The action of gamma on C2 is free outside the origin. So the space of gamma orbits here is smooth. It has one singular point, namely the origin. So you can resolve the singularities here. That gives what's called the minimal resolution. So this is a smooth space equipped with a map to the singular space, which is an isomorphism outside the singular locus. Since the singular locus here is a single point, if you want to understand this space, I mean, the most interesting thing to understand is what gets mapped to it. And in this case, what happens is quite neat. So the preimage of the singular point under this resolution is is a union of two spheres, a union of CP1s. And there's one for each vertex in the finite Dynkin diagram. So if you look at this diagram, but you forget the 0 node. So for each of these vertices, for each non-trivial irreducible representation of gamma, there's a P1. And these P1s, so you can ask how they intersect. And they intersect exactly the way this graph tells you they intersect. So if they intersect transversely in a single point, and otherwise they're disjoint. And they intersect transversely in a single point precisely when there's an edge between the corresponding vertices here. So in other words, you can get these Dynkin diagrams geometrically by considering the preimage of 0 in this resolution. So, okay, so now the basic question that I want to spend the next 10 minutes explaining is what this geometry has to do with this Heisenberg algebra. So starting from a finite, they're both things you can get starting from a finite subgroup of SL2C. So what do they have to do with each other? So in order to tell you that, I need to introduce one more piece of geometric input. So say for k greater than or equal to 0, so let's let C2 mod gamma. So this is a smooth manifold of real dimension 4. So if I put upper bracket k, that's what's known as the Hilbert scheme of k points on this space. So I mean, the precise definition of this space is not so important. How you should think about it is the following. Well, if you have this space and you have a non-negative integer, one natural space to consider is the kth symmetric product. So this is, you just take k copies of a space and you divide by the action of the symmetric group Sk, which permutes the factors. So this space has singularities. And if you look at the locus where points collide here, the space has singularities. And this is a resolution of this space. So the Hilbert scheme of k points is a smooth space which resolves the singularities in the symmetric product. So informally, a generic point here is just an unordered k tuple of points on your 4 manifold here. But when points collide, interesting things happen, which resolve the singularities in this space. Okay, so these Hilbert schemes show up. They also can be thought of as showing up as they're examples of moduli spaces of instantons on these 4 manifolds, and they show up. So they show up in differential and algebraic geometry in a bunch of places. And the philosophy in studying these spaces is similar to the philosophy you see when you study representations of symmetric groups, which is you should not consider the Hilbert scheme of k points on this space for fixed k in isolation. You should consider them for all k together. So whatever geometric property you're interested in this space, you should consider all k together and see what sort of extra structure emerges. So for example, so here's an example of a sense in which that's a useful perspective. So one can consider, so instead of looking at the, so instead of just considering the, say, singular cohomology of this space by itself, for fixed k, we consider the direct sum over all k. When k equals 0, the k equals 0, I just mean this is just defined to be a single point. We take the singular cohomology of all Hilbert schemes together. So this is a graded vector space. I mean, it's actually a bigraded vector space. One of the gradings is the cohomological grading, but let's forget about that for a moment. This space is graded just with the obvious z grading telling me which space I'm considering. So inside here, for example, there's a particularly interesting subspace. So these spaces can be considered as algebraic varieties, but we're working over the complex numbers, so they can also be considered as symplectic manifolds. And from that point of view, it's interesting to look at things like Lagrangian sub manifolds. So the middle dimensional cohomology is a natural thing to consider. So and the middle dimensional cohomology in this case is 2K. And so so if you consider the, well, so I mean C2 is symplectic, and there's an action of gamma which preserves the symplectic form. And so that gives you a symplectic structure on this space, and which actually induces a symplectic structure on all of these. Yes, that's right. Yeah, that's right. That's right. That's right. It agrees with this. Yeah. So you can also construct this space as a hyperkähler quotient. So I mean, it has a lot of different symplectic forms. So if you consider, so what's the graded dimension of this space? Well, if you compute it, this is a theorem of Gutsche. So take the dimension of well, it's the dimension of the Fock space representation of the Heisenberg algebra. It has the same graded dimension. The number of vertices that you need. Say again? So the Euler character, so all cohomology here is actually an even dimension. So you mean the graded dimension of the entire cohomology in this case? Yeah, it's actually, well, I'll come to that in a second. It's also a natural thing to consider. It's I mean, it's kind of, it looks more like the size of, so this was the vertices in the finite Dinkin diagram where you remove the zero node. So if you consider all cohomology, it looks like the size like you've added the extra node in. So it has an extra factor. But I'll explain that in a bit. OK, so let me back up. So we started with a finite subgroup of SL2C. So to this subgroup, there's a Heisenberg algebra, which has a canonical representation, the Fock space, which has this graded dimension. On the other hand, starting from the same finite subgroup, you can consider the Hilbert scheme of points on the associated minimal resolution and consider its cohomology. And the graded dimension is the same graded dimension. So, so that suggests, something which is in fact true. So all this, I mean, these observations were collected by various people in both physics and mathematics sometime around the early 1990s. What this suggests is that actually, you know, the direct sum, well, this space here, the direct sum of this middle cohomology, is in fact the Fock space representation of the Heisenberg algebra. It suggests that the Heisenberg algebra should actually act naturally here in some way. It suggests that the Heisenberg algebra acts on the cohomology of Hilbert schemes. That there's this kind of fantastic symmetry when you consider all of these Hilbert schemes together that you would not see if you considered a fixed k in isolation. Okay, and of course this is true. This is a theorem of Nakajima and Grojnowski. Theorem. This is Nakajima and independently Grojnowski. Well, that's exactly what I said. The H gamma acts on, actually it acts on the entire cohomology of all of these Hilbert schemes. And inside here, if you just look at this, the piece, the middle homology piece, this is the Fock space representation. So of course, the entire cohomology is larger than the Fock space, but you see the Fock space representation here. So, and so what's the idea in the proof? Of course, I mean, for this to be interesting, the action, the Heisenberg algebra action, should somehow be geometric. And so what Nakajima and Grojnowski do, and there are many other examples in representation theory where similar things are done, and this was not the first. Well, this is generated. It's generated by some AINs with some relations. So to each AIN, they associate a correspondence, a subvariety inside the product of two Hilbert schemes. Two different Hilbert schemes. So if I'm looking at the element AIN, it should move me from the cohomology of this Hilbert scheme to the cohomology of this Hilbert scheme. So they write down some explicit correspondence. And any such correspondence gives you a map from gives you a linear map from the cohomology of one factor to the cohomology of the next factor. Namely, take a cohomology class here, pull it back, that's a cohomology class in the product, intersect with the fundamental class of your correspondence, that's a new cohomology class in the product, and then push forward. That gives you a cohomology class here. So in this case, with these correspondences, all of those operations are well defined. And so what Nakajima and Grojnowski do is they write down a collection of correspondences and then check that the induced maps on cohomology satisfy the defining relations in the Heisenberg algebra. So it's a bit mysterious. It's not that you kind of see for some obvious perspective that the Heisenberg algebra is sitting as symmetries. It's not like that at all. You have this presentation, which may or may not be the most natural presentation of this algebra. And to each generator, there is a correspondence. And these correspondences satisfy the relations you want. So it's a fantastic construction, but I think it's in some ways a mysterious one. So of course, it also suggests some other questions. I mean, one can consider so this theorem, by the way, this is sometime around 1995. I mean, cohomology is not the only thing one can consider associated to these spaces. For example, instead of cohomology, one could consider lots of things, including algebraic K-theory. Or maybe C-star equivariant algebraic K-theory. So let me say what this is. So let's forget the C-star for a moment. So
there's a question.
Yes?
So in the case of C2, this cohomology is supposed to be like adding endpoints to your original.
Yes, that's right. So actually, that's the case in here as well. So the way the I comes in, so remember, the vertex I is one of these P1s sitting inside the surface. So the correspondence is exactly what you say. So it's an incidence variety. So you've taken its pairs, point here, such that the difference is supported at a single point, and that single point lies on the ith exceptional P1. Yeah. So okay, so one could consider, I mean, there's a reason why I haven't told you what these correspondences are, which will become clear. So one could consider algebraic K-theories. So what is this? This is a vector space, which in this case actually has the same size as this vector space, but it can be defined in several ways. So it's the growth and decay group of a category. So one category you could consider is you could consider the category of vector bundles on this space. So, and then you can write down a vector space, which is just, so namely you take a vector space, so it's the vector space spanned by, you take a vector for each vector bundle on your space. So for each vector bundle. And then mod out by the relations that A plus B equals C when the vector bundle A direct sum B is isomorphic to the vector bundle C. So then this gives you a finite dimensional vector space, which actually has the same size as this in this case. And if you didn't, now vector bundles are actually not the best thing to work with here because they don't form an abelian category. So in fact, you could replace vector bundles by coherent sheaves. And then instead of saying you mod out by A plus B equals C when you have this relation, you say mod out by A plus B equals C when you have an exact sequence. That will give you an isomorphic vector space. Actually, there's one more step which is even a little better to consider. So you can consider the bounded derived category of coherent sheaves. So this is not an abelian category anymore. You can't talk about exact sequences. But it is a triangulated category, so you can talk about exact triangles. So in particular, you could take a huge vector space with spanned by a class for each object in the bounded derived category of coherent sheaves. And then you could mod out by the relation A plus B equals C whenever there's an exact triangle like this. And yeah, in this case, there's a finite resolution of yeah. Sorry, maybe I don't understand the question.
If a vector bundle is extension of two vector bundles,
yes.
it might be a non-trivial extension. Then if you define K groups by direct sum, the middle thing could not be the sum of the two extremes.
Yeah, that's why that's why I only defined that when you were only considering vector bundles as the object.
Even for vector bundle, you can have a non-trivial extension.
Yeah, yeah. So yeah, so I think in this case it's the same size. But in any case, I don't want to consider vector bundles. I want to consider bounded derived category of coherent sheaves. So yeah, I understand the question. And I think in this case it's true, but I have to think about it. OK, so this is a space one wants to consider. So you could, and of course, if there's an action of C star on everything here, you could consider the equivariant setting, where you consider objects in the equivariant derived category. The only thing that's nice about this is now everything here will be a module over the C star equivariant K-theory of a point, which is, well, if I pass to the field of fractions, is functions in Q. So rather than working over vector spaces over C, we have space over functions in Q. So it gives a Q deformation of the entire story if you include equivariance. Say again? Yeah, so in fact, so you could also consider the Fukaya category of this. And I think the Fukaya category of this symplectic manifold has Grothendieck group, which is also isomorphic to this space. But I'm not sure about that. Philosophically, if you didn't want to work with bounded derived category coherent sheaves, you should be able to work with the Fukaya category. In particular, these correspondences are Lagrangian correspondences. So it makes sense, but I don't know what theorems are true in that context. OK, so we know the Heisenberg algebra is the symmetries of cohomology. So you can ask, what's the symmetries of, say, equivariant K-theory? So the question which was posed immediately after doing the work on cohomology is sort of, so what acts on the C star equivariant K-theory of all of these spaces? So and then there was kind of an explicit conjecture by analogy with other constructions in geometric representation theory. I think this conjecture was first formed by Nakajima, but I think it was also made by other mathematicians. So the conjecture is that, so what acts on this space is the Heisenberg algebra, the larger Heisenberg algebra, associated to the affine Dynkin diagram. And if you work equivariantly, then everything is Q deformed. So actually, it should be some kind of quantum version of this Heisenberg algebra, where you Q deform the relations in the Heisenberg algebra. So there should be some quantum Heisenberg algebra which acts here. That was the conjecture. And the reason that you might make such a conjecture is, well, the proof almost seems to be staring you in the face. I mean, Nakajima and Grojnowski write down correspondences here. Those correspondences give maps on cohomology, but they also give maps on equivariant K-theory. So you should just check what relations these correspondences satisfy, and hopefully what they'll satisfy is sort of some Q-to-form version of the relations in the Heisenberg algebra. So, so that may or may not be true. I don't know. And the reason why this conjecture is difficult to prove from this point of view is essentially technical in nature. I mean, doing computations, you have these correspondences are highly singular. When n is 1 or minus 1, they're smooth. But when n grows, these correspondences are highly singular. And you can do computations in cohomology more easily than you can do computations in K-theory. So it's just extremely difficult to check what relations these satisfy in K-theory. So even though you have this kind of nice conceptual guess for what should be there, it's difficult to check. OK, so this was more or less the kind of state of the subject in the 1990s. So what I want to do in the remaining time is explain to you how to prove this conjecture, because the proof uses some kind of slightly more modern perspective on these sorts of constructions. So, okay, so suppose for a moment that you believed that I mean, don't worry about the Q so much. We could always forget the equivariance. So suppose you believe for a moment that this Heisenberg algebra acts on the K-theory of all of these Hilbert schemes. This is different K's. Maybe I should use a different letter. Well, no, you don't need equivariance for hat. Just so the number of exceptional p1s on the surface is the finite Dynkin diagram. But if you look at the structure, so technically in K-theory you should put the line bundle O minus 1 on each of those p1s. But if you consider the structure sheaf of the entire pre-image pi inverse of 0, that gives a new linearly independent class in K-theory, and that's the extended node. So there should be operators corresponding to this class as well.
So you're considering the spaces C2 over gamma, but the Heisenberg algebra is not supposed to act in general on the cohomology of the Hilbert scheme?
Yes. So if you consider an arbitrary quasi-projective surface, then there is an analogous construction. But for example, there's no obvious guess for what acts on equivariant K-theory in that case. I mean, yeah, you're right. There's no need to restrict to these surfaces. I mean, it's kind of for the purposes of. Yes, it has to be a surface. If you consider Hilbert schemes of threefolds or things like this, then it's, I mean, they're singular and it's a much more complicated story. Yeah.
But equivariant structure comes from the action of C2, so you're using something specific about this C2 just to define the equivariant structure. Right?
Yes, that's right. That's right. So, okay, so suppose for a minute you believe that this Heisenberg algebra should act on K-theory. Well, I mean, it's kind of silly to be considering K-theory from this point of view because there's a much richer structure sitting behind the scenes that you've just forgotten about, which is the bounded derived category of coherent sheaves on these spaces. So, I mean, this is a vector space. This is a category. It's got objects, but it also has morphisms between objects. And you threw away a tremendous amount of information when you passed from here to here. On the other hand, geometrically, if you look at correspondences like this, these also give functors. I mean, in this context, they're called Fourier-Mukai transforms. They give functors between derived categories of coherent sheaves here and here. So it makes sense to ask what kind of categorical object is acting as symmetries of this richer object. And of course, if you can understand this, if you can answer this question in a good way, then I mean, you'll recover whatever you want acting on K-theory just by passing to the Grothendieck group. So this is kind of an easy question to pose, but sort of in the mid-1990s, it maybe wasn't quite so popular to ask these questions. Now it's very popular to ask these questions. So And it's also an example of one of these things that happens not infrequently, which is, it might seem to you at first glance as though this is a harder question to answer because there's more structure. But if you throw in enough structure and the structure is rich enough, you have less choice, and somehow it's maybe easier to figure out what's going on.
And here it just the ordinary derived category, or you need higher homotopy as a DG story?
No, just ordinary derived category. There should be DG versions of all this, but that hasn't been worked out. Okay, so now what I want to do is, so this is the problem that that Sabin Kaudas and I worked on. So in the rest of the talk, I want to tell you a little bit about what this categorical object is. You could think of this as a categorification of the Heisenberg algebra, or the Heisenberg category. So I want to tell you what it is and maybe say a little bit about how it acts here. So what kind of object should this be? Well, you need, each of these directions tells you some structure you need. On the one hand, this should be a category, so it should have some objects, and it should have morphisms. And maybe we want it to be an additive category so that you can, in other words, you want it to allow direct sums so that you can pass to the Grothendieck group. And one thing you want is that the Grothendieck group of this category should be the Heisenberg algebra. That's your first non-trivial requirement. Of course, maybe there's lots of categories whose Grothendieck group is the Heisenberg algebra. How do you know if you have a natural one, if you have, in some sense, a right one? Well, it should appear somewhere else in mathematics. So the other non-trivial thing you want is that you want this category acts here on something that you also independently care about. So those are the kind of two basic requirements you might ask in order to say that you have a good categorical object. You don't need one here. So if triangulated categories are forced on you if you pass from the Heisenberg algebra to the affine Lie algebra. So that's this kind of secondary step of the story, and there you have no choice but to define triangulated categories. But here it's not necessary. So I want to tell you the definition of H gamma. The point here is that instead of thinking about an algebra with generators in certain relations, we'll just have, very little structure on objects, and all of the interesting structure will be in the space of morphisms, which enforce isomorphisms of objects, which give you the relations you want. Okay, so what is this category? Well, so first I'll define an auxiliary category. I'll just put a prime here. So this is going to be a monoidal category, an additive monoidal category. So monoidal category means that, so additive category means if I've got some objects, I can take their direct sums. And monoidal means if I have some objects, I can take their tensor products. So it's generated, it has very few monoidal generators, generated by some symbols, pi. You have one generator for each vertex in the affine Dynkin diagram. So just one generator, one thing which I'll call pi, one which I'll call qi. And the monoidal category generated by these guys is everything in this category. So instead of pi, sometimes I'll draw a little upward pointing arrow labeled I. Instead of qi, I'll just draw a downward pointing arrow labeled I. So an object of this category is a finite direct sum of finite sequences in these little up and down arrows. For example, this would be another way of writing the tensor product of pi with qj with pk. So the empty word is the unit for the monoidal structure. It's the identity. So the objects are not very interesting. In particular, note that the edges in the Dynkin diagram have played absolutely no role in the definition of objects. The interesting structure comes in the morphisms. So morphisms are defined as, the reason we draw these things in pictures is we define our morphisms as planar diagrams, which so planar diagrams modulo relations. So what I mean by planar diagrams modulo relations, so a morphism from, say, pi qj to some other A morphism, I'm reading from bottom to top, from this object to this object is just a collection of immersed one-manifolds which match up with the boundary condition. So you have a collection of immersed one-manifolds. There could be some closed things here, sitting out here, and these one-manifolds are allowed to. Also, I can draw some dots on these pictures, which I'll explain in a moment. But so basically, a picture like this is a morphism from here to here, and then composition of morphisms is just stacked diagrams on top of one another. So if you want to, so explicitly what the morphisms are is they're generated by the following simple pictures. You can have a crossing, or you can have cups and caps in arbitrary orientations. J, right? Now this is, you can have a dot, which I think I'll draw as a red. If I and j are connected in the Dinkin diagram, then the defining object pi and pj, there's a morphism there. So I would need to input as a defining morphism, a morphism from pi to pj when I and j are connected by an edge in the Dinkin diagram. And similarly, I need a defining morphism, maybe I'll draw as a blue dot, from any generator pi to itself. So arbitrary morphisms can all be built from gluing together these sorts of pictures. So these guys are the generating morphisms in my monoidal category. Okay, so without imposing any relations on morphisms, this category has huge Hom spaces. I mean, so it would just be a completely unwieldy object. You need to impose some relations on morphisms. So I need to tell you when two pictures represent the same morphism in my category. And the relations come in two forms. I mean, there's two kinds of relations. So relations amongst morphisms come in two forms. The first, and the two, these are for very different reasons. So the first is planar isotopy rel boundary. And the second is local relations, which I'll write down. So planar isotopy rel boundary means if I have two pictures which are isotopic in the plane relative to boundary, then they define the same two morphism. I mean, this is, and if you're going to organize the morphisms in your category by drawing pictures in the plane, you'd better have something like this, because otherwise you can't understand what you're doing. Okay, so I'll explain that a bit more in a moment. And the second is local relations. So there are, in many, many other geometric settings, you can organize morphisms in your category in a planar diagram which satisfy planar isotopy rel boundary. The extra local relations you need to impose will depend on the circumstance you're dealing with. So these relations are very specific to our setting of Heisenberg algebras, Hilbert schemes. This first one is not really about Heisenberg algebras, Hilbert schemes. It's more general reasons. But okay, so these are the. Well, let's write up. So these are the for completeness. These are the local relations, which I'll say something about in a moment. But quickly, so I want to explain what planar isotopy rel boundary means. It's popular currently to draw pictures in these sort of categorified settings, and there's a good reason for it, which is that it encodes something natural categorically. So, for example, let's look at this planar isotopy. So what is this really saying? So the left-hand side is the identity morphism of the object pi. That's the right-hand side. The left-hand side is a composition of two morphisms. It's a composition of a morphism which goes from pi to, in the middle here you have the object pi, qi, pi. And then you map back to pi. So this equality, this planar isotopy, is just a shorthand way of declaring that this composition should be the identity morphism of pi. And this composition is, of course, just given by this cap here and this cup here. Sorry. Whoops. This is the wrong way. This cup and this cap. And of course, similar isotopies for example, for this is also equal to well, let's similarly, if I drew a downward pointing arrow, there we go. This is another planar isotopy, which tells you the same thing for qi. Qi, pi, qi. Qi should be. So exactly. So this is requiring this is exactly just a restatement of this phrase, pi is left adjoint to qi. So requiring planar so the meta principle here is if you have a collection of functors which you're interested in for whatever reason, and those functors come in adjoint pairs. So actually here we have all possible orientations. So it means in fact p is both left and right adjoint to qi. In other words, biadjoint. So if you have collections of biadjoint functors, then you should organize the morphisms between such functors in pictures in the plane, because the fact that you have a junction morphisms tells you that those morphisms will be sensitive to planar topology, that isotopic diagram. So that's why, I mean, that's essentially why these pictures are, why we draw pictures as opposed to writing down kind of horrible algebraic formulas. So I think this is kind of it's a useful idea. I mean, I don't know to whom to attribute this graphical observation, but it's quite useful. So the second relations are local relations, which I've written up here, which are just specific to our particular needs, and I should highlight. I want to highlight the upper left two for a moment. So if I didn't put labels on the bottom, this means that it holds independent of whatever the labels are. This relation, the graphical relation, always holds. So just look at these two. So these are the relations in the symmetric group, right? You square across. This says the square of the crossing is the identity, and this is the Meister 3 relation, the Braid relation in the symmetric group. So what these two relations guarantee is that the okay, and I mean a general morphism is a formal linear combination of such pictures. So what these relations guarantee is that the group algebra of the symmetric group sits inside the endomorphism algebra of pi to the n in our category, because the crossings will satisfy those relations. So if you forget dots and you forget cups and caps and you just look at the kind of diagrams you draw, you'll have exactly a copy of the symmetric group sitting inside your endomorphism algebra. This is true for any. It doesn't matter what I put here. Oh, yes. So this, well, the picture to make sense, the starting and ending labels have to match up. So yes, I mean this could be I and I, and this could be J. This is fine.
Oh, that's fine.
Yes, this is also fine. I mean, so this is I mean a very special case where the statement I wrote here is just the special case where all strands are labeled by the same I. But this more general relations hold in the category. So, all right, so this defines some sort of, I don't think it's particularly enlightening to see these relations. So remember, this is a category that I called H gamma prime. So you could ask how H gamma prime is related to the Heisenberg algebra. And H gamma prime, as it's defined right now, has no hope of having a Grothendieck group, which is the Heisenberg algebra, because it has far too few objects. The Heisenberg algebra has countably many generators, and AIN for any non-zero integer n and any vertex. The objects in our category, and so you take arbitrary products of these. Here we just had finitely many generators, pi and qi, one for each, and took their products. So you have far too few objects. But there's a way to enlarge, the natural way to enlarge the category by saying very few words. So if you think, which is just to declare that idempotent endomorphisms in our category split. So for example, you pretend you're in the category of vector spaces. If V is a vector space and E is an idempotent endomorphism, then E splits your vector space into a direct sum of two possibly smaller vector spaces. So you can do the same thing kind of formally in this category. You can just declare that idempotent split. So in particular, so that's the category which you call H gamma. It's the idempotent closure of this category H gamma prime. In particular, any idempotent in here will split this object. So the way that objects split into indecomposable objects is governed essentially by the representation theory of the symmetric group. So, okay, so that's the category H gamma. It's the idempotent completion, it's the idempotent closure, where you just declare idempotence to split, of the category defined by planar diagrams with these local relations. Okay, so then I essentially told you what the theorem about this object is. So, theorem. This is so the first is that the Grothendieck group of this category is isomorphic to the Heisenberg algebra. The Grothendieck group of this category inherits an algebra structure from the monoidal structure here. Yes, with complex coefficients. That's right. I mean, you don't have to. You could consider just the free abelian group, and then it's an integral form of the Heisenberg algebra. There's no torsion. So the second statement. I mean, okay. So that's kind of neat because it tells you in some sense you understand the objects in this category. It's not at all clear how rigid asking for a category with this property is. That might not be a very rigid question. So I don't really have a good understanding of how, I mean, the feeling is in some sense this is rigid, but I don't know exactly what extra conditions you should write down to give something rigid. But a non-trivial check that this guy is at least a natural one is the fact that it acts here. So this category acts on bounded derived category of coherent sheaves on all these systems. What does that mean? Well, what is the definition of an action of this category on this category? What it means is that to every object here, you need to assign an endofunctor of this category. Let's call this category big F. So you need to assign an endofunctor. And to every morphism here, you need to assign a natural transformation of functors. So the data you write down in order to define a categorical action of this category is a bit different than what you'd write down if you were writing down a representation of the Heisenberg algebra. Here, for a representation here, for every element in your algebra, you'd write down a linear endomorphism. And there's countably many such things you need to write down and countably many relations you have to check. Here the situation is, in some sense, simpler. The number of functors you have to write down is finite. The price you pay is that to every planar diagram, you have to write down a natural transformation of such functors. And then you need to check that all those natural transformations satisfy all of these relations. Yes, that's right. That's right. Okay, so that's the content here. So in particular, as a corollary, you get this action of the Heisenberg algebra on K-theory. Now, if you want to Q-deform the whole situation and consider equivariant K-theory, what that corresponds to here is noting that actually the Hom spaces in this category are graded. Every picture here can be assigned an integral degree, so all the vectors, and then if you consider, and then you have a grading shift functor on the category, which just shifts the grading. At the level of Grothendieck group, you call that multiplication by Q, and that Q deforms your setting. So to check these relations? Yeah, so it's not easy. In particular, it's very difficult to do geometrically. But you can replace this by an equivalent algebraic problem. So there's it's called the Mackay correspondence of Bridgeland-King-Reed. It tells you that this category is equivalent to the bounded derived category of modules over some finite dimensional algebra, which is actually the smash product of some finite group with a polynomial algebra. This algebra is a Cazul algebra. And so if you pass the Cazul duality, this is equivalent to bounded derived category of modules over some actually finite dimensional algebra. So if you, instead of working here, you can equivalently work with complexes of modules over an explicit finite dimensional algebra. And then actually, once you've passed here, the action of this category actually doesn't, I mean, it actually preserves the category of modules. So you don't even need derived categories anymore. So you just consider the category of modules here. So the way we check all these relations is there's some finite dimensional algebra, and if you actually look at projective modules over that algebra and bimodules, you can write down bimodule maps for each picture and check. And then the bimodule maps, you can check whether or not they're the same. And then by some sort of complicated equivalences, that gives you connection here. Well, OK, of course, there's plenty more to say, but maybe this is a good place to stop.